In this channel we will be designing footing for Revit software for structural modeling from 1-story building to 200 floors. All formulas are programmed for easily exploration for various parameter to derive the footing size and rebars details. If we try 100 floors with load tributary of 4 meter by 4 meter, with assumed design parameter, the size of square footing will be 8.125 meters and depth is 1.175 meter. To check in one ways shear is OK and check the two-way shear ISOC main bars is 24 number of 32 mm diameter bottom bars both ways with the spacing of 313.35 mm. If any are not sufficient to resist the loads, if we try 50 floors with load tributary of 4 meter by 4 meter, with assumed design parameter, the size of square footing will be 5.75 meters and depth is 1.175 meter. To check in one ways shear is OK and check the two-way shear ISOC main bars is 17 number of 32 mm diameter bottom bars both ways with the spacing of 316 mm. If any are not sufficient to resist the loads, we will check the formulas. If we try 50 floors with load tributary of 4 meter by 4 meter, with assumed design parameter, the size of square footing will be 5.825 meters and depth is 1.175 meter. To check in one ways shear is OK and check the two-way shear ISOC main bars is 28 number of 25 mm diameter bottom bars both ways with the spacing of 184.26 mm. If any are not sufficient to resist the loads, we will check the formulas and RCD codes, although we can check it in structural software, but we must understand first the theoretical manual approach. If we try 75 floors with load tributary of 5 meter by 5 meter, with assumed design parameter, the size of square footing will be 9.3 meters and depth is 1.175 meter. To check in one ways shear is not okay and check the two-way shear. ISOC main bars is 44 number of 25 mm diameter bottom bars both ways with the spacing of 187.21 mm. If any are not sufficient to resist the loads, we will check the formulas and RCD codes, although we can check it in structural software, but we must understand first the theoretical manual approach. If we try 10 floors with load tributary of 5 meter by 5 meter, with assumed design parameter, the size of square footing will be 3.4 meters and depth is 1.15 meter. To check in one ways shear is okay and check the two-way shear. ISOC main bars is 16 number of 25 mm diameter bottom bars both ways with the spacing of 190 mm. If any are not sufficient to resist the loads, we will check the formulas and RCD codes, although we can check it in structural software, but we must understand first the theoretical manual approach. Dead loads are include the self-weight of structural members, such as walls, plasters, ceilings, floors, beams, columns, and roofs. Dead loads also include the loads of fixtures that are permanently attached to the structure. Dead load is 117.72 kN. Live load is that can change over time, such as when people Live load is that can change over time, such as when people are walking around in a building. Anything in a building that is not fixed to the structure. In this example we have live load of 32.31 kN cals kilogram. Conversion for visualization. We'll assume that the floor load is 4.78533632 kN per square meter or kilopascal. The depth is 2 meter. And we have slab on grade thickness is 150 millimeter. Assume the thickness T is greater or equal to 300 millimeters. The compressive strength of concrete varies from 2500 psi, 17 MPa, to 4000 psi, 28 MPa, and higher in residential and commercial structures. In our example is 25 megapascal or meganewton per square meter. The yielding strength of reinforcement is 415 megapascal. We have 250 kilopascal ultimate bearing soil capacity. This value can be seen in soil report, and factor safety is 316 mm diameter bar. The unit weight of concrete is 23.544 kilonewton per cubic meter. Considering soil bearing pressure, the KNA is equal to Q ultimate divided factor safety, so 250 divided by 3 equal 83.34 kilopascal. Nominal soil bearing pressure is equal to 83.34 kN minus 4.78533632 minus 23.544 times 0.15 for slab on grade pressure minus 20 times 1.7 for soil pressure above footing, so on so forth, so the Qn equal to 33.96 kilopascal. This is sample only of footing that there is length, width, and thickness and reinforcing bars, but our example is square footing that y the width and length. This the actual layout of footing reinforcement, top and bottom bars as shown, and column rebars. See the other videos. Prior to pouring of concrete, formworks at side of footing is required. Here in 3D view I will show to you the B as width is 1.5 meter, then the length is also 1. The factor load equal 1.4, dead load equal to 59.332 kilonewton. The X equal to B over 2, minus C over 2 minus D. So X equal, as shown, then actual V shear is VOA equal ultimate soil bearing. Check one way shear as per rebars section and dimension D, dB, clear covering of 75 mm based on code exposed to earth, and T is equal or greater 500 mm as assumed thickness, so D equal thickness minus clear covering CC minus dB diameter of bar, so depth D equal to 405 mm. In this drawing, square footing width equal to length B, the punching shear of X, D, C/2, B/2 as shown. Calculating the ultimate shear capacity is VUC equals P times 0.17 times square root of FC times big B times D. By substitution the value, it is equal to 199.85625 kN greater than 26.74 kN. Therefore, OK. Since it is not OK, we use the formula shear VUC as capacity is equal or greater than VUA actual to calculate the depth D as shown. So by substitution equal to 0.75 times 0.17 times square root 25 times 1500 times divided 1000 to kilonewton meter equal 45.58 times 1.51.5 minus 0.3 over 2 minus over 1000. So depth D is 40.04, then to thickness T is 131.04. Round up the thickness to 25 mm is 150, then recalculate the depth is equal to 59 mm. This is our width and length of footing equal to B, so punching shear width is C square plus DD over 2 Checking the two ways shear in actual is VUT is equal to KNU time B square minus C plus D square. By inputting the values, now the result is 96.68060402 kN as actual shear. The perimeter bow is equal 4 times C plus D, so bow is 1.436 meter. Beta is calculated as per code is the ration of long side of column to short side of column. The shear capacity at equation in the code is 0.75 times 0.33 square root 25 times 1436 times 59 times 1 over 1000. To convert same unit at other side equation equal 104.85 kN. Shear capacity at B is equal to 0.17 times 1 plus 2 over 1 times 0.75 times square root 25 times 1436 times 59 times 1 over 1000. So the result is VUC at C is equal 0.75 times 0.083 times 2 plus 40 times all over 1436 square root 25 times 1436 times 59 times 1 over 1000. To convert kilonewton is equal 96.08 kilonewton. Least punching shear is 96.08 kN greater than actual shear, so not OK. If not OK, we will use the equation punching shear VUC capacity equal or greater than VUA actual. So by substitution VUC equals 0.75 times 0.33 times square root 25 times 4 times 300 times depth, then divided by 1000 to convert kilonewton equal to or greater than VUA. Using quadratic equation as shown, so we calculated depth D is 302.85714212910.3. To be depth D greater or equal to 302.86, so thickness is 397.86 plus 75 clear covering plus 16 bar diameter, so thickness of footing will be 397.86 to round off. To be depth D greater or equal to 302.86, so thickness is 397.86 plus 75 clear covering plus 16 bar diameter, so thickness of footing will be 397.86 to round off to 25, just divide by 25 then round up then multiply by 25, so it is become 400, then depth will be calculated to 305. So again take the least of three equation required in code. Equation is 542.01, equation 2837.64, equation 3, so the least shear capacity is 542.01 compared to actual 94.22, so the shear capacity is less than shear actual, so it is okay. Check again for one-way shear. Again using calculated depth D is 305, using shear actual equation is equal to 20.17, then shear capacity is equal to 291.66 greater than 20.17, so it is okay. As per drawing, the failure plane is here with distance x or width b over 2. The center of column toward x is c over 2, so ultimate moment mu is equal to kno times b times x over 2, so the mu is 12.31 kilonewton meter. Use this formula to calculate a based on ultimate moment is equal to or less than P times 0.85 times Fc times AC times D minus A over 2. And the strain of concrete greater than 0.005 mostly, and Fs of steel is greater the phi, and P is 0.90. Ultimate moment is 12.31 times 1000 to power 2 to convert to kilonewton millimeter, equal or less than 0.9 times 0.85 times 25 times A times 1500 times 305 minus A over 2. So to calculate A using quadratic equation, A is equal to 1.42. Hashtag div/0. Hashtag div/0. As per diagram, compression C is equal to tension T, then the C is equal to 0.85 times Fc times A times B is equal to as area of steel times phi, so as is equal to 0 mm, and as minimum from code is equal to 1193.58, therefore us as 1193. To calculate number of bar is equal to as over pi over 4 times d times b to power 25.94, round up to whole number becomes 6 nos of 16 mm diameter of main reinforcement bar. To spacing of rebars 1500 equals 6 number times 16 bar diameter plus 275 clear cover times 2 both side plus 6 number minus 1 times SSO spacing is equal to 250.8 mm. As per the code must be lesser to 3, which is 1193.58 and 450 mm, so it is okay. For temperature or shrinkage bars, same with the number of main reinforcement above, so 6 numbers 16 mmo shrinkage or temp bars spacing is 250.8 m, therefore use 6 number 16 bottom bars both ways. If we try 1 floors with load tributary of 4 meter by 4 meter, with assumed design parameter, the size of square footing will be 2 meters and depth is 0.4 meter. To check in one way shear is OK and check the two-way shear is OK. Main bars is 8 number of 16 mm diameter, bottom bars both ways with the spacing of 246 mm. If any are not sufficient to resist the loads, we will check the formulas and RCD codes, although we can check it in structural software, but we must understand first the theoretical manual approach.